Okay, today we're going to take a quick review of Newton's laws. Newton's first law, which we sometimes call the law of inertia, says that objects in motion stay in motion at constant speed and direction, and objects that are not moving will not move unless a force is applied to them. So for this example, if you really want to something that's moving really wants to travel in a straight line at constant speed. So if you throw something like a baseball, the reason it curves down and hits the ground is because gravity is pulling on it and it pulls it down, and then friction will slow and eventually stop the object. If there was no gravity and no friction, it would just move in a straight line at constant speed. That's kind of what the planets do. It's the closest example I can give you that's something that's been moving for a long time, and that's our planets. They've been going for 4.5 billion years without stopping because there is no friction to slow them down in space. They don't go in a straight line, though, because the sun's gravity pulls them into that circular path. But if the sun were to magically disappear and every planet would just go in a straight line out into the universe and never be seen again. Newton's second law, which we say is force equals mass times acceleration, also sometimes written as acceleration equals force divided by mass. All this law does is explain the relationship between force, mass, and acceleration. It's good to think of it like a balanced seesaw where both sides of the seesaw have the same value. So force is on one side, mass times acceleration is on the other side. If we just throw some numbers in there, if the force on the object was 200 newtons and the object had a mass of 20 kilograms, then the acceleration would be 10 meters per second squared. So 20 times 10 is 200, and kilogram times meter per second squared is what we call a newton. So both sides of that are equal. If we change that, if we were to get a heavier object, one that had more mass to it, but we were using the same force, we're still using 200 newtons, but now the mass of that object is 100 kilograms. Look at how I made the m bigger. Then the acceleration, 100 times what is going to equal 200? It's 2. So the acceleration is only going to be 2 meters per second squared now. So that's why I made that a smaller. They're still equal. It's still 200 newtons of force, but because the mass got bigger, the acceleration is less. You could think of that as if you've ever had to try and help push a car that ran out of gas. I know you guys are young, but my son had to do it one time with my wife because she ran out of gas. Fortunately, the car did not have a lot of mass to it. It was a small car. So my son was able to push it into the gas station. They were just at the gas station when it happened. They got really lucky. If the car was a bigger, heavier car and he tried to push it, it might have gone a lot slower or not even at all if he didn't have enough force to be able to move it. On the opposite side of that, if you're using the same force, if the object was a lot lighter, had less mass, you would get more acceleration, which is kind of what I said with the car example. Less mass means you can push it faster. Now, those examples were if the force was to remain the same. We can also look at it as what would happen if we changed the amount of force we used. So if the force increased on the left side of the equation, then on the right side of the equation, one or both of those things has to increase also. If the object doesn't change, if it's the same thing we're pushing, like the small car, and we used more force, we would get more acceleration. It kind of makes sense when you think of it that way. Finally, we get to Newton's third law. Newton's third law, which is sometimes what we call the action-reaction law, says that for every action, there is an equal but opposite reaction. So Newton was explaining why you don't fall through the floor if gravity is constantly pulling down on you. Gravity doesn't stop because you're standing on the floor. Gravity's always pulling down on you. That's why you have weight. If you were to step on somebody's foot or you step on a toy and break it, it's because of your weight. It's because of gravity that's making you do that. So when you're standing on the ground, why aren't you moving if there's a force acting on you? That's because the gravity pulling you down is balanced by the ground applying a force in the opposite direction, and that force is equal. This is why they're balanced forces and why you don't move down or up for that matter. It would be kind of scary if the ground applied more force to you then you would go flying up in the air. And it might be funny to watch somebody else do that, but it wouldn't be fun for you. Now, this has probably happened to everybody at some point in your life. You're walking around and you don't see the coffee table and you hit it with your knee. The way we would sometimes explain that, we'd say, I hit the furniture with my knee and the furniture hit me back. This is just Newton's third law. An example there. If you apply a force to the coffee table applies a force back to you, and that hurts. This also explains how rockets and planes fly. If you have a rocket ship or a jet engine, that burns fuel and it creates this exhaust gas. And because the exhaust gas is expanding very rapidly, it has a greater volume than the liquid fuel did, that gas gets pushed backwards at high speed. So the engine pushes the gas back. The gas pushes the engine forward. And that's how they fly. It's action-reaction. Now, I don't know how they got this picture, but I love ending a video with a good cat example of Newton's third law. Face-to-face, action-reaction. Ouch. Stay safe, everybody.